What's up, everybody? This is Matt Brown with another IoT hacking video. Today I have a TP-Link Tapo home security camera that we are going to perform a glitching attack on in order to gain access to its bootloader. And that will grant us a root shell on this device. So let's go over to our desk like we always do and get started. So here you can see that I had a 2-pack of this camera, so this is what it looks like before you break it open. And I have the basic components here. There is a motor that allows the camera to swivel, and I don't have that connected up to the camera. I only have what is necessary to power the device. And so let's look under the microscope because we're going to do a little bit of information gathering that's going to inform the rest of our analysis of this device. So we're going to look under the microscope here, zoom out a little bit, and the first thing we're going to look at is the largest chip on the board, and that is, we can see here that it is a Q star SSC333. So here, and you can even see that it says ARM, so that's likely telling us that this is an ARM-based CPU, which it does turn out to be. That is true. And so this is the CPU of this device, and it is a Linux-based device, spoiler alert. And so what we're interested in is this identifier here, because what we can do is when we're doing hardware hacking on a device like this and we want to learn more about this chip, is what we want to Google, what we want to search on the internet for is this model number, that identifier there. And then just some other reconnaissance on the board that we're not going to get into in this video because we kind of addressed it in a different video, is this flash chip on the other side. We're not going to be reading the firmware directly off this chip, but we will be interfering with this chip's ability to be read by the CPU. And we'll get into that a little bit later. But right now what we just want to understand is this is an 8-pin chip. And we can actually zoom in, and if I can get the angle just right, you can see the identifying marking. This is an XMC 25QH64C flash chip here. And so that is going to allow us to also identify the data sheet for this device as well. So with that, let's quickly go over to my computer screen here and look at these two data sheets for these two different components that we found on the board. So first I have the CPU data sheet pulled up here, and I have navigated to the pin diagram that tells us the description of all of the pins. And this chip, as you can see under the microscope, we can actually access all of these pins without desoldering this chip from the board. It's not like a BGA chip, a ball grid array chip, when most of the connections are underneath the chip. That would require us to either find where those points are connected elsewhere on the board, or we would have to remove the chip. In this case, we can gain access to all of these pins without removing the chip, which is nice for our purposes. And so what we're interested today is UART. So UART is a serial interface that often exists on a Linux system. And if you haven't done much hardware hacking before, what you want to think of when you think of UART, it's like if you're spinning up a Linux box, if you're spinning up some system that doesn't yet have a graphical interface installed on it, but you plug a monitor into that system, you're going to get just a terminal kind of output, right? A really basic interface that you can interact with the device. Well, that's what UART's going to provide. And so what we're going to see when we later connect up to this UART interface is that it's going to print out the booting of the device from the bootloader, and then booting into the Linux kernel, and then the underlying userland Linux system on our device. So we want to be able to connect up to this UART interface, and on this pinout diagram, you can actually see a couple different UARTs mentioned. That's because often when peripherals are connected to a CPU, those also use UART communication. So we see a kind of false positive over here on pins 43 and 44. Let me make this bigger so you guys can see. That turns out to not be actually our UART interface, but over here we have PM UART RX and PM UART TX. So those are going to be the transmit and the receive lines for our UART interface. And again, those two lines are the important ones, and then we need a connection to ground, and those three connections should allow us to both receive data from the UART interface and transmit back to it if transmission is allowed, which sometimes it might be allowed, sometimes it might not be allowed. Little foreshadowing for what we're going to see on our device there. But before we go away from that, I want to look really quickly at this flash chip. And so here we can look and we can see. I think I just got to scroll down here and find where our chip is listed. Here it is. And so here we can see the pin description from all 8 of those pins on our flash chip. Now this is a pretty like standardized pin out here. So if you have an 8-pin SOIC SPI flash chip, they're probably going to be the same, but it's very good for us to be able to refer to the specific data sheet that we see for the device on our PCB. And so we're going to leave this up and we're going to come back to it because it's going to become very important later when we perform our glitch of this flash chip. So let's first go ahead and let's go and get UART connected up and just see that interface working. So we're going to hop back over to our desk. So I'm going to pull this away for a second. So we already identified that the pins are going to be located on this corner of the chip. Now this is way too small for you to see. We're going to zoom in with the microscope in a second. But what I want to show you is this setup that I have over here. So I have a UART cord off screen, and it's something that looks like this. I have another one, and all it is a USB interface. And then on the other side, we have these connectors. There are actually 6 connectors here, but again, like I mentioned, only 3 signals are really going to be important for us. We need the transmit, the receive, and ground. And so on this cable and a lot of other cables like this, yellow is usually going to be the receive for our cable. Orange is going to be transmit, and then black is going to be ground. And so you'll see over here, I have that color coordinated with these 3 pogo pin PC byte probe setup. So this is going to allow me to connect up to our board, and we'll be able to see this better under the microscope. We're going to be able to connect to all these signals, and that is connected up to my UART cord. And by the way, that all is assuming that this is a 3.3 volt UART interface. And so we could look in the documentation, but let's just go verify that really fast. So we're going to pull up our microscope. We're going to turn on our multimeter here and put it into voltage mode. And so I'm going to find ground, which is going to be slightly off the microscope. Oh, actually, I think I can connect right here. I think this will be a valid ground signal. And then I'm going to turn on this device. I'm going to power it up. And then I'm going to connect over here, and we can see that we are indeed at 3.3 volts on that connection. And then we're going to try our other pin on this other side, which we read from the data sheet. Oh, and see, we can see that voltage fluctuation there. That is that telltale sign that this pin right here is the transmit pin from the CPU's UART interface, right? Because the way that it sends data is it sends a digital signal by varying the voltage between 0 volts and 3.3 volts. And obviously this multimeter is not fast enough to switch you know, it doesn't have the resolution to kind of pick up that signal. So that's why you're kind of seeing an average of something in the middle. And so that is pretty cool. And again, we're able to verify that our 3.3 volt UART cable is the correct choice for us here. So now what we're going to do is, so since we determined that this right here is our transmit pin, I'm going to be connecting, so you can kind of see here, the yellow probe up to that one, because we want to have the transmit and receive flip-flopped. So the transmit of the board is going to go to the receive of my cable and vice versa. And so I'm going to very gently put this other one right here. And then my black cable is going to be slightly off camera because I have an easier connection to ground. Over on the other side. Okay, so we should be all connected up there. And now going to go over to our screen. Okay, our device is powered off currently. And so what we're going to do is we're going to open up our terminal here, and we can get rid of our multimeter overlay. So what we're going to do here is we're going to run Picocom. That's just a terminal emulator program. And then we're going to connect it up to, you can see, dev TTY USB 0. That is the device node that my USB to UART cable identifies as. And then you can see the -B flag, a baud rate. We're assuming the default baud rate of 115/200. That's the most common baud rate for any Linux-based IoT devices. Sometimes you'll see different ones, but that's what you always want to guess at first, and it is going to be the right guess in this case. So we got that set up. Now let's go over here and let's turn on, and we are seeing that we get into that we have this output of this UART interface, and I'm hitting the enter key on my keyboard. And you notice that nothing is happening right now. And trust me, that connection is correctly set up, and I'll be able to prove that because now that the device is booting into the full Linux OS, we will see my keyboard get a response. So I'm connected correctly up to the receive pin of the CPU with my transmit. But during the bootloader, the boot up of this device, it is not responsive, right? So on most of these Linux devices, the bootloader is going to be U-boot. It's an open source bootloader. And it is going to, it's going to allow, by default, it allows you to hit enter or hit any key, and it will pause the boot process. It won't boot into the operating system or run its boot process or anything like that. And it will present you with a menu and let you edit a bunch of boot settings. But they have locked that out on this device. But what we're going to do is we're going to perform a glitch that will not allow the flash chip to be read out at a certain time in the boot process, and that will cause U-boot to freak out and say, I don't know what's going on, and drop into that menu that will allow us to control the device. So let's turn the device off and let's set up this glitch. And while we're here at our computer, we're going to talk about how we're going to set up that glitch. So we said we have this pinout right here for our flash chip. And so what we're going to do is we have the ground here at pin 4, and then we have data out. So data out is what it sounds like. The data is going to go out of the flash chip from this pin to the CPU when it wants to read something that's inside of the flash chip. And so that's what we want to ground that pin out at a certain time. We want to be able to ground it at a certain time in the boot process and stop stop it from being able to read successfully, and then cause it to do something unexpected, which in this case is drop into that bootloader menu. So that's what we're going to do. Let's go back to our microscope because we got to solder up some wires. So what we got to do, so I'm going to take all my probes off. I'm verifying that I have in fact turned off the device, and we're going to go back over to that flash chip. So you can kind of see I've already got some solder on on a couple of these these pins because I've been playing with this. All right, so what I'm going to do is we're just going to throw a little bit of flux. Here's pin 2 and 4 over here. And it's just all going to go everywhere. I'm going to turn on my air extraction because I don't want to breathe in flux fumes because that would be bad. And then I'm going to introduce just a little bit of solder just so we get some good fresh solder on these 2 connection points. And now we've got these 2 wires here. Solder 1 onto pin number 2. If I can get my hands steady here. That is the question. Nope. That's not happening. Wow. All right, I need to cut this wire a little bit is what I'm going to do. That's kind of acting weird. Actually, I'm going to put more solder. I don't know why the solder's like... Hey, there we go. All right, that's a big clump of solder, and I will make sure at the end of this that I haven't bridged these connections. Because again, I don't want to glitch it out the whole time. I just want it to glitch when I touch these 2 wires together. So I'm soldering them on. All right, that is not the world's best soldering joint, but it will probably be okay for the purposes that what we're doing today. Again, not the world's best soldering joint, but we have soldered to pins 2 and 4 successfully. Going to turn off my air extraction. Done with that for a little bit. And now we're going to flip ourselves over. So I've got those 2 wires off to the side here. And so what I'll be able to do is, if I can show it on screen, is I'll be able to touch these at a certain point in the boot process that will allow us to mess with it. So now we just have to get situated here. We're going to put my, going this way, connecting my probes back to TX and RX. Okay, now I'm doing the ground, which again, you can't see, it's off screen. Got it. Check. Okay, it looks like TX and RX are still good. Now what we're going to do is we are going to perform a sanity check here where, okay, so yeah, it's turned off. I'm going to perform a sanity check that TX and RX are still connected and that it will boot fine when I am not glitching. So to do that, just powering on the device. It powers on. Okay, and we can actually talk about where we're going to glitch. And this is told to me by somebody else. That second time where it prints out audio negotiate, right there. That's when we're going to initiate our glitch, because that's when it says like reading from the flash chip. Because what we don't want to do is we don't want to screw up the loading of the U-boot bootloader, because then all games are off and we're going to get a crash or something like that, right? Okay, so looks like we're still good. Something I want to show you that we will definitely run into here. Where is it? Well, I'll show you guys later, but there's definitely some problems with entering text into the console. Specifically, if I try to paste, you'll see sometimes it does like capital letters instead of lowercase letters. And so that is a problem, but the copy and paste does work. it's just not echoing it back properly. And I don't know why. And I've checked my ground plane a bunch of times. But when you're doing weird glitches like this, sometimes you get weird results. But now let's try this again. And again, all I'm doing here is I'm preparing these 2 wires that I have here that we showed. We soldered onto pins 2 and 4 of our SPI flash chip. Then I'm going to wait. Okay, that's the first auto negotiate. We don't glitch yet. And then second one. Okay. Now I'm bridging our pins. This is what I want to see. And we've dropped into a bootloader menu. There we go. All right. So, done soldering. Get those gloves off. All right. So now we are into our bootloader menu here. And so, you're kidding me. Did I bump? I bumped one of them, didn't I? No, it's this one that would be wrong. Oh yeah, it's totally off the pin. Aha, there we go. Okay, I bumped it when I was doing my glitch. All right, so here we can type help, and we can see the standard kind of U-boot options here. And so probably one of the first things you want to run if you're trying to like hop into a shell is you want to print the environment variables, because most of the time there will be this environmental variable called boot args. So what we're going to do is we are going to prepare, let's just come over here in Vim. We're going to prepare a new set of boot args. And so the way we're going to do this is this command, set env, the way it works is we're going to go like this. It's set env space the name of the environmental variable space the rest of the stuff, right? And so we want to change one thing in here, and that is the init variable. So instead of running etc pre-init, which if you're not familiar with what init is, so first when a Linux system boots, it boots into the kernel, and the kernel sets up a bunch of cool stuff, space magic stuff that happens inside of kernel land. And then the kernel transfers control to user land. And the first thing it runs in user land is whatever you provide to this init variable. And so instead of running that first thing, what we're going to do is we're going to run bin sh. We're going to run a shell. So that way it's not going to put us into a login prompt. It's going to put us directly into a shell environment. So now that we have that set up, I'm going to paste it in, and you can see that looks terrible, right? Like, it looks like it didn't copy that right, but I promise you that it did. And then I'm going to say run boot cmd. It's going to run our boot command. I think you can also run boot, but I'm just following it. Okay, following a tutorial that I found. Okay, and now we have a root shell. Okay, so we are root. But by default, there's not a lot of stuff set up in here. So what we can do now is that etc pre-init thing, we can now run that init system. Now, on some devices, your mileage may vary, but in this device, this works perfectly. And this actually gives us access to the device functioning, as far as I can tell, 100% normally. Some devices you do this to, you will have a problem where it won't initialize everything. You might need to go find some kernel modules, find something else that mounts all the correct file systems. But in this case, if we run etc pre-init, it actually mounts all the file systems correctly, and then it starts doing a bunch of other stuff that is like the initial, stuff that the camera needs to do. We might see some output here. Let's get rid of this. But there you have it, right? So now what we can do is we can manipulate the system, and what we could do if we wanted to get persistence on this device is we could look for writable file systems and then write some piece of data into there. Maybe look for a writable password or shadow file to put a password hash into the system. Unfortunately, on this device, the password hash is stored in a squashfs file system, which is read-only by design. You can't actually modify a squashfs file system. You would have to modify it and then like re-flash it to the flash chip. So that would be a chip off firmware modification, which we might do in a new video later on. But for now, the cool thing is that this system is actually going to be running most of the stuff that it needs to run the camera. And so we're root, we can look around the file system, we can do a lot of things because we were able to glitch that flash chip and use the bootloader as a way to get us a root shell, whereas before, when we booted into the device in the UART interface fully, it only gave us that login prompt where we needed to know the username and password. So thank you for watching this video. I thank everyone for watching these. Please comment down in the comment section what kind of stuff you like in these videos, what you'd like me to change, any new content ideas, and be sure to check out our Discord where I will post live stream information. Sometimes I've been live streaming where we actually kind of did the same glitch during the live stream, and that inspired this video. So thank you for watching. Have a good day.